Hello and welcome to our deep dive into the fascinating world of modern power systems. Today, we're exploring a critical component of our energy future, multi-terminal high voltage direct current or MT-HVDC systems, as we push for a greener planet, integrating large-scale renewable energy sources like wind and solar farms, often located far from our cities, becomes essential. MT-HVDC systems are the superhighways that make this possible, transmitting vast amounts of power over long distances with remarkable efficiency. They connect multiple points, creating a flexible and robust power network. But with great power comes great responsibility. The stability of these complex networks is paramount. A single fault, like a short circuit on a transmission line, can trigger a cascade of failures, potentially leading to widespread blackouts, if not handled immediately. This is where fault detection comes in. It's the nervous system of the grid, designed to identify and locate problems with lightning speed. Ensuring the reliability of MT-HVDC systems isn't just an engineering challenge. It's crucial for maintaining the backbone of our modern society. In this video, we'll dissect the sophisticated protection strategies that keep these systems running smoothly. We'll start with the first line of defense, the primary protection schemes designed for ultra-fast response. Then we'll look at the crucial backup systems that step in when the primary methods fail. We'll also venture into the cutting edge of research, exploring how artificial intelligence and advanced signal processing are revolutionizing fault detection. By the end, you'll have a comprehensive understanding of how we protect these vital energy arteries, making our power grid more resilient and ready for the future. So let's get started. When a fault occurs on an HVDC line, the first few milliseconds are critical. Primary protection schemes are all about speed. The goal is to detect and isolate a fault before it can destabilize the entire system. One of the most effective and widely used primary protection methods is based on traveling waves. Imagine a calm pond. If you drop a stone into it, ripples or waves travel outwards from the point of impact. A fault on a transmission line creates a similar effect. But instead of water ripples, it generates high-frequency electromagnetic waves of voltage and current that travel along the line in both directions at nearly the speed of light. These are the traveling waves. Detectors or relays installed at each terminal of the transmission line are constantly monitoring for these waves. When a fault occurs, the wavefront reaches the nearest terminal first. The relay at that terminal detects this sudden change and can almost instantly recognize it as a fault signature. By measuring the arrival time of the wave and sometimes the polarity of the initial wavefront, the system can not only detect that a fault has occurred, but also get a good estimate of its location. This time domain analysis is incredibly fast, often identifying a fault within just 2 to 5 milliseconds. This rapid detection allows circuit breakers to open and isolate the faulted section before the fault current rises to dangerous levels, protecting expensive equipment and preventing system-wide instability. The elegance of the traveling wave method lies in its intrinsic speed, making it an indispensable first line of defense for long HVDC lines. Building on the concept of analyzing sudden changes, another powerful primary protection strategy involves transient analysis using advanced signal processing techniques. While traveling wave methods focus on the initial wavefront, transient analysis takes a broader look at the high-frequency disturbances that a fault introduces into the system's voltage and current signals. Think of the normal, steady-state operation of an HVDC line as a pure musical note. A fault is like a sudden, jarring noise that disrupts this harmony, introducing a cacophony of different frequencies. The job of transient analysis is to listen for and identify this noise. Two of the most prominent tools for this are the wavelet transform, or DWT, and the Hilbert-Huang transform, or HHT. Let's start with the wavelet transform. Unlike traditional Fourier analysis, which breaks down a signal into its constituent frequencies across the entire signal's duration, the wavelet transform provides a time frequency analysis. It can tell you not only which frequencies are present, but also precisely when they appeared. It uses small, wave-like functions called wavelets to scan the signal. When a fault occurs, it creates high-frequency transients. The wavelet transform is exceptionally good at capturing these short-lived, high-frequency events, which appear as large coefficients in the wavelet analysis. By monitoring these coefficients, a protection relay can detect a fault with incredible precision and speed. The Hilbert-Huang transform, or HHT, is another sophisticated technique, particularly well suited for analyzing nonlinear and non-stationary signals, which are common during power system faults. The HHT first decomposes the complex fault signal into a set of simpler components called intrinsic mode functions, or IMFs, through a process called empirical mode decomposition. Each IMF represents a basic oscillation within the signal. After this decomposition, the Hilbert transform is applied to each IMF to obtain instantaneous frequency and amplitude information. A fault will cause abrupt changes in these instantaneous characteristics, creating a clear signature that a protection system can recognize. Both DWT and HHT allow us to extract detailed features from the transient signals that are invisible to simpler methods, enabling ultra-fast and reliable fault detection, forming a cornerstone of modern primary protection. Now, what happens if the primary protection system fails to operate? This could be due to a relay malfunction, a communication error, or a particularly unusual fault type that the primary scheme doesn't recognize. This is where backup protection comes into play. Backup protection is the safety net of the power system. It's designed to be completely independent of the primary system and operates if and only if the primary protection fails to clear the fault within a set time. While primary protection prioritizes speed, backup protection prioritizes reliability and certainty. It might be slower, but its job is to ensure that a fault is cleared no matter what. Without effective backup protection, a single point of failure in the primary system could lead to catastrophic consequences. Let's explore the first layer of this safety net: conventional overcurrent and overvoltage protection. These are some of the oldest, most time-tested methods in power system protection, and they still play a vital role in backup schemes for HVDC systems. The principle is straightforward. The system continuously monitors the current flowing through the transmission line and the voltage at various points. Under normal operating conditions, these values stay within a well-defined range. A fault, especially a short circuit, causes a dramatic surge in current and a corresponding drop in voltage. Overcurrent protection is designed to trip a circuit breaker if the current exceeds a predetermined threshold for a specific duration. To provide coordination and prevent unnecessary trips for temporary issues, these relays often have an inverse time characteristic. This means the higher the fault current, the faster the relay will operate. Overvoltage protection works similarly, but monitors for excessive voltage levels, which can occur under certain fault conditions or during switching operations, posing a threat to insulation and equipment. While simple and robust, these methods have limitations, especially in complex MT-HVDC systems. Their main drawback is their relative slowness compared to primary schemes. They need to wait for the current or voltage to reach a clear and sustained fault level, and they often include intentional time delays to coordinate with other protective devices. This delay, while necessary for reliability, means they aren't suitable for first-line defense. However, their simplicity, low cost, and independence from complex algorithms or communication channels make them an essential and dependable backup, ensuring that even if the sophisticated primary systems fail, the fault will eventually be cleared, safeguarding the grid from collapse. Another robust backup protection method is differential protection. This technique is based on a fundamental law of physics, Kirchhoff's current law, which states that the sum of currents entering a node must equal the sum of currents leaving it. In the context of a transmission line, this means that under normal conditions, the current flowing into one end of the line segment should be exactly equal to the current flowing out of the other end. The differential protection scheme leverages this principle with remarkable effectiveness. Here's how it works. Current transformers are installed at both ends of the protected line segment. These devices measure the local current and send this information to a differential relay. The relay digitally compares the magnitude and phase angle of the currents from both ends. If the line is healthy, the two currents will be virtually identical, and their vector difference will be close to zero. However, if a fault occurs anywhere between the two measurement points, some of the current will be diverted to the ground or the other conductor. This creates an imbalance. The current flowing into the line will no longer equal the current flowing out. The differential relay will detect this difference, or spill current. If this difference exceeds a set threshold, the relay concludes there is an internal fault and issues a command to open the circuit breakers at both ends, isolating the faulted line. The great advantage of differential protection is its selectivity. It only responds to faults within its defined zone of protection between the two current transformers. It is inherently immune to faults outside this zone, which prevents incorrect tripping during disturbances elsewhere in the grid. While traditional differential schemes relied on dedicated communication channels to compare currents, which could be a point of failure, modern implementations are becoming more advanced. However, due to this reliance on communication and the need for precise time synchronization, it's typically used as a backup scheme in HVDC systems. Its a high reliability and clear operating principle make it an excellent complement to the faster primary methods, providing a secure second layer of defense. The world of power system protection is not standing still. In fact, it's undergoing a revolution, driven by the explosive growth of artificial intelligence and machine learning. These intelligent methods are moving beyond fixed rules and thresholds, instead learning to recognize the subtle and complex patterns of faults directly from system data. They promise to deliver protection schemes that are faster, more accurate, and more adaptive than ever before. Let's start with artificial neural networks, or ANNs. Inspired by the structure of the human brain, ANNs consist of interconnected layers of neurons that can be trained to recognize patterns. In fault detection, an ANN is fed a massive dataset containing numerous simulated or recorded fault scenarios. This data includes raw voltage and current waveforms, or features extracted from them, using techniques like the wavelet transform we discussed earlier. During training, the network adjusts the connection strengths between its neurons until it can accurately map specific input patterns to the correct output. For example, classifying the condition as no fault, line to ground fault, or line to line fault, and even estimating the fault's location. Once trained, the ANN can analyze real-time data and make a diagnosis in a fraction of a second. Its ability to learn from complex, non-linear relationships in the data makes it incredibly powerful for identifying faults under a wide variety of system conditions. Another popular machine learning approach is the use of decision trees, and their more powerful variants like random forests and gradient boosted trees. A decision tree works by creating a model that predicts the value of a target variable by learning simple decision rules inferred from the data features. It's like a flowchart of yes or no questions. For instance, a tree might first ask, is the peak current above a certain value? And then, is the high frequency wavelet coefficient above another value? By following a path of such questions, it arrives at a final decision about the fault type. Decision trees are intuitive and fast, but the real power comes from combining many of them into a random forest, which improves accuracy and robustness by averaging the predictions of multiple trees. These AI-based methods represent a paradigm shift, moving from pre-programmed logic to data-driven intelligence. To make these intelligent systems even better, researchers are employing sophisticated optimization algorithms. The goal of an AI model, like a neural network, is to be as accurate as possible, but its performance depends heavily on its internal settings, often called hyperparameters. Finding the best combination of these settings can be a monumental task. This is where optimization algorithms come in. Think of them as intelligent search methods that help the AI model find its optimal configuration. One fascinating example gaining traction is the Harris-Hawkes optimization algorithm. This is a nature-inspired meta-heuristic algorithm that mimics the cooperative hunting behavior of Harris hawks. In the wild, these hawks work together to surround and flush out their prey. The algorithm translates this strategy into a mathematical search process. Different hawks in the algorithm represent different potential solutions. In our case, different sets of hyperparameters for a machine learning model. They explore the search space, share information, and cooperatively converge on the best possible solution, much like the hawks cornering their prey. By using an algorithm like Harris-Hawkes optimization, we can automate the process of fine-tuning our AI-based fault detectors. This leads to models that are not only more accurate, but also more efficient. They can be trained faster and can achieve better performance than models tuned manually by human experts. Other optimization algorithms, such as genetic algorithms or particle swarm optimization, are also used for similar purposes. The key takeaway is that optimization is the secret sauce that helps unlock the full potential of machine learning and power system protection, ensuring our intelligent systems are operating at peak performance. The synergy between AI and optimization is pushing the boundaries of what's possible, creating a new generation of highly effective protection schemes. Beyond the realm of AI, innovation continues in the field of signal processing itself. Researchers are constantly developing new techniques to extract clearer fault signatures, especially in challenging conditions. One such advanced technique is the Tiger-Kaiser Energy Operator, or TKEO. This is a simple yet powerful non-linear operator that can estimate the instantaneous energy of a signal. What makes it so special for fault detection? Its ability to track rapid changes in both the amplitude and frequency of a signal simultaneously. When a fault occurs, it releases a burst of energy that propagates through the transmission line. The TKEO is exceptionally sensitive to this sudden release of energy. By applying the TKEO to the voltage or current signals measured at the relay location, we can generate a new signal, the Tiger energy profile. Under normal conditions, this energy profile is low and stable, but at the very instant a fault begins, the energy profile exhibits a massive sharp spike. This spike is a clear and unambiguous indicator of a fault. One of the key advantages of the TKEO is its robustness, particularly for high-impedance faults. High-impedance faults, also known as high-resistance faults, occur when a live conductor makes a poor connection to ground, for example through a tree branch. These faults produce very small fault currents and can be incredibly difficult for conventional overcurrent or even some transient-based methods to detect. They are like a whisper compared to the shout of a direct short circuit. Because the TKO is so sensitive to the sudden change in the signal's energy, it can often detect the subtle signature of these high-impedance faults where other methods fail. This makes it a valuable tool for enhancing the sensitivity and reliability of protection systems, ensuring that even the most elusive faults are caught before they can cause significant problems. As we've seen, the protection of MT-HVDC systems is a multi-layered and rapidly evolving field. We began with the primary protection schemes, our first responders, traveling wave methods, and advanced transient analysis using wavelet and Hilbert-Huang transforms provide the essential speed, detecting faults in mere milliseconds to prevent system instability. They are the vigilant sentinels, watching for the first sign of trouble. Then we explored the crucial role of backup protection, the safety net that catches what the primary systems might miss. Slower but incredibly reliable methods like conventional overcurrent and overvoltage protection, along with the highly selective differential protection schemes, ensure that a fault will be cleared, no matter what. This layered defense-in-depth strategy is the bedrock of modern grid reliability. But the story doesn't end there. We are on the cusp of a new era, defined by intelligence and data. The rise of machine learning, with tools like artificial neural networks and decision trees, is transforming protection from a set of fixed rules into a dynamic learning system. These AI models, honed by powerful optimization algorithms like Harris-Hawk's optimization, can identify fault signatures with unprecedented accuracy. Combined with advanced signal processing tools like the Tiger-Kaiser energy operator, which enhances detection of even the most subtle faults, our ability to protect the grid is becoming more sophisticated every day. Looking ahead, the future of grid protection is undeniably intelligent, data-driven, and increasingly communicationless. New schemes are being developed that can make autonomous decisions using only local measurements, reducing reliance on potentially vulnerable communication links. This trend is crucial for building the next generation of power grids that are not only more efficient and capable of handling massive amounts of renewable energy, but are also fundamentally more resilient and self-healing. The work being done in this field is essential to powering our world safely and sustainably. Thank you so much for joining me on this detailed exploration of HVDC protection. I hope you found it insightful. If you enjoyed this video and want to learn more about the cutting-edge technologies shaping our energy future, be sure to like, subscribe, and hit that notification bell so you don't miss our next video. Until next time, stay curious.